Welcome to the lectures on high voltage engineering. In this lecture video, we are going to study the generation of high AC voltage using the concept of resonant transformer. Now, what is meant by this resonant transformer and how we are able to generate the high voltage using such type of circuit configuration, we are going to study in detail in this lecture video. Normally, in a high voltage engineering, we require high voltages. We require high voltages in our labs, in our test labs, so that we can test the objects. We can test the insulators. Okay, so in this type of circuit, we will be using the concept of the resonance, and we will generate resonance. What does it mean? First, let's look on the circuit diagram of the of our test bench or the lab equipment. Here we have the input AC power supply. Here we have the transformer. Here we have the inductor. Now, this inductor is also known as the additional choke, and this type of inductor, it is a such type that it is adjustable. We can adjust the value of inductance of this inductor. And what is the C? This is the capacitance, and this is actually the model of the test object. What does it means? What are our test objects in our high voltage labs? Our test objects are normally the insulators. And insulators are when we apply the high voltage across the insulators, they behave as the capacitors. They have the capacitance properties in them, and insulators are typically the low power dissipation component, or insulators occur actually the low power dissipation. So this capacitance is the equivalent electric model of the test object which we are going to test. So this is the practical model of the high voltage generation using resonant transformer. Now, the important thing to understand is this, the concept of resonance. What is meant by resonance? Because this is, in fact, the resonance is in the circuit is here, which is creating the high voltage. This transformer has a little role in stepping up the voltage. Actually, there is the circuit resonance, which is responsible for generating the high voltage across this test object. I repeat, the resonance of this circuit is actually responsible for creating or generating the high voltage across this test object. To understand it in more detail, let's first construct the equivalent model of the this circuit, or you are familiar with the equivalent circuit model of the transformer. We are going to replace this with the equivalent circuit model of a transformer. Okay. So an equivalent circuit model of a transformer comprises of which type of components? You are familiar with your study, with what you have studied in your electric machines, that the equivalent circuit of a transformer, the model or the equivalent circuit model of a transformer comprises of the following components, as I am drawing here: the resistance of the primary winding, the self-inductance of the primary winding, then we have the magnetization branch, which represents the resistance, and this is actually modeling the eddy current losses, and then we have the inductor in the magnetization branch, which is actually which models the magnetization current or the hysteresis losses as well. And this is the equivalent circuit model here. And then we have the resistance of the secondary winding, and then we have the inductance in the secondary winding. So in fact this is the equivalent circuit model of this transformer which we are gonna which we have normally, the transformers we have, and this is an additional choke, and here you have capacitor. Now as I told you that the circuit resonance is actually responsible for creating high voltage across this test object. Now what is meant by circuit resonance? As you are well aware that if you have an inductor and capacitor and there is a switch between them, let's say once we charge this capacitor, and when we turn this switch on, what happens? The currents flow in this inductor, and when this but inductor, you know, it opposes the change in current. So what it will do, it will create the positive potential here and negative here. But when the current tends to decrease, the inductor opposes the change in current. Yes, since inductor will invert its polarity and the energy will flow in the capacitor, and this flow of energy continues between this inductor and capacitor. So obviously there we will be having the current and the voltage here. Now what is this voltage? You can derive it using the concept of network analysis. In fact, what's going on here? Here we have, you can see that here we have an adjustable choke or an adjustable inductor. What we do, and you know that what we have to do, you have to adjust this value of additional choke or the inductance L such that this circuit starts resonating. Well, as you know that these resistances, now look now focus here, that these resistances are very small. Okay, so what we are left with, this inductor and capacitor circuit. Okay, ignoring these resistances because they are very low in value, we are left with the inductors and capacitance. Okay, so the circuit is just like the LC circuit, and as you know that when and how we do this, as you know, when the circuit is in the resonant condition, in the resonance condition, what happens? The inductive reactance becomes equal to the capacitive reactance. This occurs when the circuit is resonating. So XL is equal to XC. So in this case, as you know, it is equal to the omega L is equal to 1 by omega C. The resonating frequency comes out to be 1 divided by 2 pi under root LC. What we do, we adjust the value of this inductor such that this circuit goes into the resonance condition. Once the circuit is in resonance condition, these reactances become equal and they cancel each other, and the circuit impedance is now only equal to the resistance when there is the resonance. So in that case, when the circuit reaches the resonance condition, the voltage V here rises, and the voltage depends on and the equation for the voltage comes out to be V output. The voltage here, it will be equal to V by R into 1 divided by omega C. This is the output voltage, the voltage which will experience across this test object, and this output voltage is equal to the V. Now what is V? V is actually the voltage here. V is the secondary side voltage of the transformer. R, now what is R? R is the equivalent resistance of the resonating circuit. What is omega? Omega is equal to 2 pi f, you know the frequency. And what is C? C is the capacitance of the test object. Now for a moment, please stay focused on this circuit. R is the, it is, you can say equivalent resistance, or you can also say it as a total resistance of the circuit, and V is the secondary side rated voltage. And what we do, let's say if this transformer is operating at the 50 Hertz, we adjust the value of the inductance L, the additional choke, such that this circuit reaches in the resonance condition, and in the resonance condition what happens, the voltage across this capacitor rises, across this test object. Actually this capacitance is modeling the test object, and that voltage is given by this equation. And you know, and one more thing is that the quantity xc by R is equal to 1 by omega c R. Okay, so 1 by omega c R is also equal to the Q, the Q factor of this resonating circuit. The Q factor, what is Q factor? You have studied in your previous courses, the Q factor of this resonating circuit. So the output voltage, we can also write it at the output voltage is equal to the Q factor multiplied by the secondary side rated voltage of the transformer, and the Q factors are typically, it is in between 40 to 50, it ranges between 40 to 50. So what is the advantage of this circuit is that by that your primary side voltage or the required voltage is 50 times less than the voltage which is produced across this test object. Let me make another more precise or more practical diagram. This diagram is a more theoretical diagram to elaborate the concept of the resonance circuit. The practical circuit will be like that. So here we go, the complete circuit of the practical circuit of the high voltage generation using the resonance transformer. In the circuit you can see that we have a 1:1 transformer, because the transformer which we are deploying is not meant to step up the voltage, rather okay, so because the transformer which we are using here is not meant to step up the voltage, the transformer which we are actually using is its purpose is to play its role in the resonance. Okay, and so this is your input voltage as not only the resonance but also the isolation between the input and the output side, between the source side and well, its purpose is actually to generate the resonance in the circuit. So practically we have a 1:1 transformer, and this is the choke which we put it additionally here, and this is the test object. Now test object is being modeled by the capacitor, because test objects show the capacitive nature when a high voltage is applied, and this is the output voltage which we will measure across this test object. Now what happens, we have to what we do, we get this circuit into resonance condition. How? Let's say if this is a 50 hertz transformer, and this is the adjustable inductor. So you adjust the value of the inductance such that this circuit becomes in the resonance, and at the resonance X, the capacitive reactance is equal to the inductive reactance, XL is equal to XC, and this is the equation of the voltage of the resonating circuit. And this equation, you are familiar with this equation, you derived it in your network analysis course. The output voltage is equal to the V is the voltage here, this voltage across the secondary side of a transformer, divided by the omega, divided by the capacitance and the resistance. Now this is the capacitance of the test object, and this is the resistance of the circuit. It is also equal to the QV, because Q is equal to 1 divided by omega CR, and Q is also known as the and the Q factor, it tells us about the factor by which the input voltage is magnified, because when we have a resonating LC circuit, the voltage gets magnified, and the magnified voltage and Q factor tells us how much the voltage is magnified. And normally in resonant transformers, the value of the Q lies in the range of 40 to 50. It means that whatever the input voltage here, it will be raised by 50 times across the test object. So what is the benefit? The benefit is that now using this concept of resonating transformer, the required voltage is decreased by the factor of 1 by Q. And moreover, this method, since it involves the transformer as well, it provides the large current across the test object. And moreover, when the test object fails, because when the high voltage reaches here, when the test object fails, no more arcing occurs, because now this capacitance is no more there and the resonance ceases. This is what the main working of this and the concept of the resonant transformer. Now one thing you may ask, that how the input voltage rises here. As I told you, because of the resonance. And what is the concept in the resonance is that when the inductor and capacitor start to exchange their energies with each other, what happens? The current flows. And when first the capacitor is putting up its energy in the inductor, what happens? The current is in this direction, and current decreases because the capacitor is now discharging across the inductor. But inductor does what? It opposes the decrease in current or the change in direction of the current by inducing the voltage across it, and eventually because of the continuous the change in current is continuous because of this exchange of energy, the voltage accumulated here is much more. So this is the underlying reason behind the resonant transformer concept, that the output voltage is much higher than the supply voltage. So resonant transformers are also very common and typically used in our high voltage test labs in order to test the insulators. And one more thing, the insulators which we have, they actually behave as the capacitors. So let us discuss some applications of this circuit of the high voltage generation using resonant transformer. The applications are there. Such circuit is used for cable testing. It is also used for dielectric loss measurement in capacitors. This circuit is also used for the partial discharge measurements. Partial discharge measurements for cables, capacitors and insulators. So this type of topology founds three applications: cable testing, dielectric loss measurement and partial discharge measurement. So here we are done up with the concept of the high voltage generation using the resonant transformer. Nothing is difficult, just all you need, the main part is to adjust the value of the inductor such that this circuit achieves in the resonant condition. Once this circuit starts resonating, the output voltage will be equal to this equation. So thanks for your time.